Think of a digital certificate less as a static file, and more as a living identity with a full life cycle. It's born when keys are generated. It applies for recognition through a certificate request. It's officially issued and bound to an identity. It spends most of its life being used to secure connections and prove trust. And eventually it must be renewed, or retired and revoked. If you only focus on the moment a certificate is created, you miss where most real-world risk sits: forgotten expiries, unmanaged keys, and unclear ownership. Understanding this journey end-to-end is what prevents outages, supports compliance, and lets you plan PKI operations proactively, instead of scrambling when something breaks. In the rest of this module, we'll unpack each stage of the lifecycle and connect it directly to the systems you run today. In any PKI, everything begins with how you generate keys. If the keys are weak or exposed at birth, no amount of fancy certificates will save you. There are two big ideas here. First, cryptographic strength comes from three things: the algorithm you choose, the key size, and the quality of randomness feeding the generator. If your entropy is predictable, an attacker can guess or brute force the key, even if the algorithm itself is strong. Second, security depends far more on the private key than on the public key. The public key is meant to be shared. The private key is your identity. The moment a key pair is created, the private key should go straight into a protected environment and never appear in clear text, where it can be copied, logged, or backed up insecurely. Different storage options balance security and cost. Hardware security modules provide the strongest protection and are used for roots, intermediates, and other high-value keys. Encrypted vaults and files are common for enterprise and server workloads. Keeping keys only in memory is acceptable for testing, but far too weak for production. The core takeaway: strong algorithms and randomness create cryptographic strength, but disciplined handling of the private key is what actually preserves trust. When you want a certificate, the first thing you create is a certificate signing request, or CSR. You can think of the CSR as a structured plea to a certificate authority. Here is who I am, and here is the public key you should vouch for. It bundles three main elements. First, the subject information, the identity you want certified, such as your main domain name and any additional domains or service names. If those alternative names are wrong or incomplete, your certificate won't work where you expect it to. Second, the public key that will be embedded into the certificate. This is the key others will use to verify signatures or encrypt data to your system. Third, the CSR is digitally signed using your private key. That signature proves to the CA that the entity requesting the certificate actually controls the corresponding private key. The non-negotiable rule is that the private key itself never leaves your system and is never included in the CSR. Only the public key and the signature travel. Keeping that boundary intact is what preserves trust in the entire PKI. When you ask for a certificate, you're really asking a certificate authority to vouch for your identity. The process begins when your system sends a certificate signing request that already contains your public key. The CA first checks that the request is well-formed and fits its policies. Next comes identity validation. For a typical domain certificate, the CA must verify that you actually control that domain. That can be proven in a few ways. By adding a special TXT record in DNS, by hosting a specific file at a known path on your web server, or by responding from an approved administrative email address. Each method shows that whoever sent the request controls the domain's infrastructure. Once those checks pass, the CA runs any remaining policy reviews, and then uses its own private key to sign a new certificate for your public key and identity. That signed certificate is returned to you, and becomes the object other systems will trust. The key idea is that trust doesn't come from the key alone. It comes from this validation and signing process, where the CA links a verified identity to a specific key pair. Now that you've seen how a certificate is requested and issued, let's look at what happens when you actually put it to work in real systems. Deployment starts with installing the certificate and its private key in the right place. A web server, an app server, a signing service, or a client device. That private key must stay protected and should never leave that environment. Next, the system has to recognize the full chain of trust. The leaf certificate, any intermediates, and the trusted root all need to line up, so other parties can verify them during a TLS handshake or signature check. Before exposing anything to real users, you test in a staging environment. You confirm that connections succeed, that clients see a valid chain, and that legacy systems don't break. Only after that do you move the configuration into production. From the moment a certificate is in active use, monitoring becomes critical. You need to watch for expiry, misconfigurations, unexpected usage patterns, or failed handshakes, because any issue here directly impacts availability and trust. Once a certificate is deployed, the next challenge is keeping trust alive over time. That's where renewal comes in. Certificate renewal is about extending trust without interrupting service. During renewal, you usually keep the same identity information, like the subject and SANs, but you get a fresh validity period, and often a new certificate serial number. The important question is timing. If you wait until the last few days, you're in the danger zone, where any delay can cause an outage. Mature teams start planning well before expiry, and they aim to automate renewals, so they happen reliably and repeatably. Renewal also forces a few strategic decisions. Do you keep the existing key pair or generate a new one for better security? Do you need to add or remove SANs because the system's footprint has changed? And which method will you use? Manual ticket-driven renewals, or an automated protocol like Acme that lets systems request and install new certificates on their own? Handled well, renewal becomes a routine background process. Handled poorly, it becomes one of the most common causes of avoidable downtime in PKI. Not every certificate will simply live out its full term. Sometimes you have to cut trust short. That's where revocation comes in. Revocation is the kill switch of PKI. As soon as a certificate should no longer be trusted, revocation is how you tell the world to stop accepting it. The highest urgency cases are key compromise and CA compromise. If a private key is stolen, or a certificate authority itself is hacked, you must treat every affected certificate as toxic and revoke immediately. Other cases are less urgent but still important. An employee leaving the company, or a service or business shutting down. In all of these, you're cleaning up trust that is no longer valid. To communicate revocation, PKI mainly uses two mechanisms. Certificate revocation lists are periodic downloadable lists of serial numbers that are no longer valid. OCSPay is more dynamic. A client can ask, "Is this specific certificate still okay right now?" and get a real-time answer. The pattern is simple. Issuance builds trust. Revocation breaks it the moment it becomes unsafe to continue. Even if nothing is compromised, every certificate has a built-in ending, expiration. Certificate expiration is a silent, automatic failure mode in PKI. You don't have to do anything wrong for it to happen. Time alone will take you over the edge. At the exact moment the not after timestamp is reached, that certificate becomes instantly invalid. Browsers and clients don't negotiate or offer a grace period. They simply stop trusting it. Once a certificate is expired, you cannot extend its life. You must replace it with a new one. That's why expiration is often described as a cliff. Either you renew before the edge or you fall off. In practice, you see three patterns. In the best case, renewal is planned. A new certificate is issued, deployed everywhere, and traffic moves over seamlessly. In the worst case, no new certificate is available when the old one expires, and you get an immediate outage and a firefighting scenario. In between, you can have partial failures, where some nodes have the new cert and some still serve the old one, causing intermittent errors due to caching or load balancers. The key takeaway is that expiration is predictable, irreversible, and entirely your responsibility to manage operationally. To keep expiration and renewal from becoming constant manual work, modern environments rely on automation. That's where Acme comes in. Acme is the protocol that lets us treat certificates as something the system manages for us, not a manual chore. There are two main actors: a user agent, like CertBot or Cert Manager, and a certificate authority, like Let's Encrypt. The user agent proves control over a domain by answering a challenge from the CA. For example, by placing a special file on a web server or a record in DNS. Once that challenge is passed, the CA can safely issue a certificate, and the same channel is later used to renew it before it expires. The power of ACME is that all of this is automated. No logging into portals, no copying CSRs, no calendar reminders. Tools such as CertBot, Caddy, Cert Manager, or Posh Acme speak Acme for you, so certificates can be short-lived, constantly rotated, and much less vulnerable to human error. This is the foundation for secure, large-scale TLS in modern environments. By this point, you've seen each stage of the certificate lifecycle. The real question is how to run that lifecycle without outages or surprises. Think of it as a continuous loop of planning, prevention, detection, and response, all wrapped in compliance. Planning means having an accurate inventory. You should know who owns each certificate, what system it protects, and exactly when it expires. Without that, everything else becomes guesswork. Prevention is about staying ahead of problems. Renew early, not in the last week. Wherever you can, automate issuance, renewal, and installation, so you're not relying on manual calendar reminders. Detection assumes something will still slip through. Use real-time alerts for upcoming expirations or misconfigurations, and back that up with regular audits, so you catch rogue or shadow certificates. Response is your safety net when things do go wrong. Have documented playbooks for emergency renewal and revocation, and actually test your fallback plans, so you know how long it takes to recover a broken chain or an expired critical cert. Across all of this, every action has to align with your internal security policies and any external regulations. A mature PKI lifecycle isn't just technically sound, it's also provable and auditable. So far, we've focused on how the lifecycle should work. Now let's look at how it actually breaks in real environments. The first killers are boring operational issues. Certificates expire because nobody tracks them. A single missed renewal can take down a public website, a VPN, or an internal API. Equally painful is losing the private key. You can't just reissue trust. You often have to rebuild that identity from scratch. Identity mistakes are next. If the subject or SANs don't match what clients expect, you get confusing certificate not valid errors, even though the crypto is fine. Add legacy algorithms or weak randomness on top, and you've turned a trust mechanism into a liability. Then come lifecycle conflicts. Running overlapping certificates for the same service without a plan confuses both humans and systems. Forgetting to publish the full chain or misconfiguring intermediates means clients can't build a path to your trusted route. Revocation is another blind spot. If you don't have a clear strategy for revoking and checking bad certs, compromise turns into a prolonged security gap. Using old CSRs or copying configs forward can silently propagate bad data or weak settings for years. Finally, as you scale, manual processes simply don't keep up. Without automation for issuance, renewal, and inventory, even a well-designed PKI will fail under operational load. The pattern to notice: most PKI failures are not about mathematics. They're about process. Strong lifecycle discipline and automation turn these predictable mistakes into rare events, instead of regular incidents. When you operate PKI at scale, success comes down to visibility. You can't protect what you can't see. Start with a clear inventory. How many certificates you have, which keys issued them, and roughly where they live in your environment. That's your baseline. Next, expirations are your biggest operational risk, so you track them by time window. Certificates with more than a couple of months left are fine. As they move into the 30-day window, they should automatically land on a renewal backlog. Anything under a week is no longer a planning issue. It's an incident waiting to happen. You also want to monitor renewal health. Are renewals succeeding automatically, or are you seeing growing numbers of failures and manual workarounds? Spikes in failures usually mean broken automation, or policy changes that haven't been rolled out cleanly. Finally, keep a close eye on revocations. Each revoked certificate should have a clear reason, like compromise, retirement, or policy violation. Unexplained or frequent revocations are a signal to investigate your key management and issuance controls. Together, these metrics let you move from reactive firefighting to proactive PKI operations, and drastically reduce the chance of an embarrassing outage caused by a single forgotten certificate. As long as you have only a few hundred certificates, you can usually survive with manual processes, spreadsheets, and some basic checks. But as your environment grows into thousands or tens of thousands of certificates, everything changes. Expiry becomes a constant risk. Outages become more likely, and human-driven workflows simply can't keep up with renewals, key rotations, and policy checks. At this point, automation stops being a nice-to-have and becomes mandatory. You need automated renewal pipelines that talk directly to your certificate authorities and your infrastructure. You need certificate management platforms that can discover certificates, enforce standards, and give you central visibility across multiple CAs and environments. And increasingly, you reduce risk by using short-lived certificates so that even if a key is compromised, the impact window is very small. The key idea is that PKI at scale is not about doing the same tasks faster. It's about redesigning the lifecycle so that machines do the routine work and humans focus on governance, exceptions, and continuous improvement. As PKI becomes critical infrastructure, it's no longer enough that it works technically. It has to be defensible from a compliance and governance perspective. Think of regulations and standards as guardrails around your certificates and keys. Frameworks like PCI DSS, ISO 27001, and EIDAS don't just mention PKI. They dictate how you generate keys, how long they live, how you protect them, and how you prove that control to outsiders. Inside your organization, this turns into concrete rules. Who is allowed to request, which type of certificate, what key sizes and algorithms are permitted, which uses are forbidden, and how quickly issues must be fixed. Those rules only matter if you can demonstrate they're followed. That's where audits come in. You need evidence that you know where every key is, who touched it, and does. A clean chain of custody for private keys becomes just as important as the cryptography itself. Strong PKI governance is ultimately about traceability and accountability. When something goes wrong, you can show exactly what was supposed to happen, what actually happened, and who is responsible for closing the gap. Let's tie together what you've learned about the certificate lifecycle and how to keep it under control in a real environment. Every certificate journey follows the same 5 stages. First, you generate keys with strong entropy and store the private key securely. If you get this wrong, nothing else can save you. Second, you create a CSR that correctly represents the subject and includes the right public key and extensions. This is where identity and technical requirements come together. Third, the CA validates you and signs the certificate. Here, weak processes or poor vetting directly translate into weak trust. Fourth, you deploy the certificate to the right endpoints and monitor that it's actually being used as expected. Fifth, you manage endings, renew before expiry, revoke when something is compromised, and allow planned expirations when services are decommissioned. Operationally, avoid drama by starting renewals at least 60 days before expiry and automating wherever possible, typically using ACME or similar protocols. Maintain a complete, accurate inventory of all certificates, issuers, and owners, so there are no surprises. Regularly test the renewal path end to end, not just in theory. And make sure all of this is documented as clear procedures, so your PKI processes survive team changes, audits, and incidents. At this point, it's about turning theory into an actual plan for your environment. Start by understanding what you already have. Build a complete inventory of your certificates and where they live. Without that, you can't manage risk. Next, design how you'll avoid surprise expirations. That usually means automated monitoring and alerting, not a spreadsheet and calendar reminders. Then, make your renewal process boring and repeatable. Document who does what, how keys are generated, how CSRs are created, and how new certs are deployed. And don't just write it down, run tests so you know renewals work under pressure. Finally, look at where automation protocols like ACME could safely reduce manual effort and human error. Your goal is a lifecycle that is visible, monitored, documented, tested, and wherever possible, automated.